Good morning, everyone. Morning to you all. I believe you had a very lovely holiday and that you have enough energy to learn and digest the material for the beginning of the week. Okay. I hope Oda would join us in the course of the lecture. I have placed slide material in your model environment that covers the first part of the fermentation mode that we're covering. And the first, I'm going to put three materials like that. One on the batch culture system, one on the continuous fermentation system, and one on the fed batch system. That is, I'm going to put three separate set of slides for you to guide you to further understand the concept involved. Just as a reminder for those that might have missed the first lecture, I want a very interactive class. I want you to interrupt any time that you don't seem to have understood what I explained. If you have a particular aspect that's not clear to you, please feel free to interrupt. Okay, feel free to interrupt, and no questions. Nobody will be blamed for asking questions here in the class. We'll ensure that your various questions are addressed accordingly. Okay. Tereshina, just to confirm, are you able to see my screen, the entire class? Are you all able to see my screen?
Yes, sir, we can see your screen.
Great. And I really encourage everyone to always take part in the various lectures, whether via Zoom or face-to-face. Okay. I encourage you all to take part in those modules because it is an opportunity for me to explain the complex concept, and it's also the time suitable for you to ask questions on those aspects that may be a little bit complicated. Right. We started looking at something quite interesting that day. Just to refresh your memory, we're looking at this diagram that you currently have in your screen, and that was within the batch culture system. One thing we'll learn is that when you placed your inoculum, the presence of nutrient in the reactor, and you don't add more nutrient, you don't take out the product, you operate what is called the closed system or the batch system. That system goes through a number of phases or a number of stages, and you have seen some of those stages. Just to refresh your memory, you're going to have the lag phase, the acceleration phase, the exponential phase, the deceleration phase, the stationary phase, then the dead phase. Now, at the last lecture, began to have a look at how the microbes behave within each of those stages. And we stop on the deceleration phase. Okay, we stopped at the deceleration phase that day. And one important question which I asked you, or perhaps let me refresh your memory on what happened at the deceleration phase. Yeah, at the deceleration phase, basically the growth that is exponential, that is the huge growth that you observe at the exponential phase, the growth reduces, right? It gradually reduces. Since if your phone is ringing, great. The growth reduces and the cell enter the stationary phase. And just to put your memory in the context, we're referring to stage 4 on this diagram, right? This is your deceleration phase, stage 4 here. If you look at it, if you project it on the time scale, it may not last for long, but I told you it was one of the most important phases of growth as well. And the question put to you that day before you went on break was, first, I said it's important because it produces a number of products that have antimicrobial properties. Now, the question put to you is, why do microbes produce those kind of products at this phase? Why do they produce those products during the exponential phase? Who has an idea? Why will microbe produce more product that have biopharmaceutical relevance at the deceleration phase and also sometimes the stationary phase, right? That is, many of those products are produced during the deceleration phase 4 and the stationary phase 5 on your diagram. The question put to you is, why will microbes embark on the production of such chemicals at that stage? Who has an idea? What's an idea? Why will microbes embark on the production of such chemical at that stage? Okay, let me put it in this context. Currently, let's assume that we are 100 and we are locked. Let's say, of course, I don't pray that we should be locked. If you're 100, we're locked in a confined space, 100 of us here in the class. And at the beginning, we have enough pizza packed somewhere. That is, there's an excess pizza for everybody or excess food for everybody. You're going to notice something. At the beginning, when we still have enough pizza pack, everybody will be friendly to everybody. You're going to see, for example, Nolu that will be greeting CZ, how are you? I hope you are keeping well, and so on and so forth. That is, that friendliness will still exist. Right? As time goes on and we consumed those nutrients, we consume the pizza that we pack in the class, in the environment where we are. There is a scenario in which some of us will notice that very soon we're going to run out of nutrient. Therefore, there's a need to come out with whatever weapon that we have to prevent other people from surviving so that we can benefit the remaining nutrients that remain, the remaining nutrients. In other words, when microbes are at exponential phase, which is here, they have excess nutrient. They're friendly among themselves. But when they enter the deceleration phase and eventually stationary phase, they begin to sense that they begin to create competition due to scarcity of nutrients. As nutrients are reducing, microbes enter into competition. And the only way to destroy other microbes and survive is for them to produce those antibiotics, right? In other words, microbes will produce the antibiotics only when they are growing below Mumax, when they are not growing at the exponential phase. They're either at the deceleration phase or the stationary phase. That's where they produce the products that are being harvested, purified, and commercialized as antibacterial or antimicrobial. Does that make sense a little bit, Nolu? That microbes will eventually produce those products, not, I emphasize, not when they have excess nutrient. They will produce the pharmaceutical product only when they are facing starvation, only when they are reduced nutrient. If I refer it back to the analogy of the class that I said earlier on, if there's excess nutrient, all of us will be friendly. From the time that we sense that we soon run out of nutrients, competition will begin, and everybody will try to see what can he use to be the only one surviving, so that it can benefit all the nutrients, all the pizza available, right? I would like you to understand the capability of microbe of producing antimicrobial based on the fact that the depletion of nutrients lead to competition, forcing the microbes to produce those antimicrobial products. Something very important again is, if you grab this concept here, and I really would like you to grab it. You grab this concept here, you're going to understand why fed batch mode is useful to produce those antibiotics, right? Grab the concept here, the conditions, the prevailing conditions under which microbes produce those biopharmaceutical products. That will make it easy for you to understand why fed batch mode will be used to produce those kind of products. Of course, don't get me wrong. You have other products that are produced at the exponential phase. Okay? You have other microbial products at the exponential phase. Those are generally referred to as growth-related or growth-associated product. Whereas those produced at the deceleration phase and the stationary phase are non-growth related product that is produced when cells are basically not growing. Whereas those growth associated products are produced during the exponential phase and are linked to the growth rate of the cell. Having said that, one important question which will come to the mind is it possible to prolong the deceleration phase? I would like you to think about it. Is it possible that we could extend the deceleration phase? For example, you have understood that this phase here, phase 4, is quite transient, it's very short phase. But is it possible for it to extend the time that cells will spend? Okay. For example, you want to prolong the deceleration phase here, this short phase here. You don't want the cell to grow at the maximum growth rate. You don't really want them to enter stationary phase, but you want to keep them somewhere here. Is it possible to extend it, to make it longer? I'm referring to in terms of time-wise, time scale. Can the deceleration phase be extended? Who has an idea?
Okay, can I
Michael.
Input.
Yeah, who has an idea? Let me just go ahead, please.
I think maybe the addition of some nutrients, but not like in a lot, just a little amount, and then maybe the removal of some of the toxins that they, like the metabolic products that they produce.
Thank you very much.
The exponential phase.
Great. That's Dinio, am I right?
Yes, it is.
Great, Dinio. Your answer is perfect. In actual fact, what is behind fed batch culture is what you have just explained. The idea is you don't want to give them too much nutrient so that they will not be too comfortable and don't produce your antibacterial. At the same time, you don't want them to enter the stationary phase and the dead phase. You give them limited amount of nutrients. Or you can ensure to remove those parameters that are leading to the deceleration phase. For example, if the deceleration phase is triggered by the accumulation of toxic substances, if you remove those toxic substances, you can actually extend the deceleration phase. But more importantly, at the industry, what they do is that they will add limited nutrient in a control amount. That is, as a control additions of limited nutrient. Okay, write it down. The deceleration phase can be prolonged by the continuous additions, by the control additions of the limited nutrient.
Sir, but if you're removing anything, won't it not become a batch phase anymore because you're taking out something? It's not closed.
Exactly. If you begin to play around with natural fact, you're actually moving into the fed batch mode. If you add nutrient or remove, you actually move into the fed batch mode. But the idea is, if you want to extend this phase, an addition of a nutrient can create it. But that would no longer actually be a batch system. That's very nice, Uda. Now, you're going to realize that when you begin to look at the industrial production of antimicrobial, you'll understand why they are using the fed batch mode, why they are adding nutrient gradually, where the system has reached the end of exponential phase. Okay, you're going to see that they're going to use the fed batch mode to produce those products, those antimicrobial, in which the system will be triggered to the fed batch and there'll be gradual additions of nutrients in a control amount. Great. Now, eventually cells will enter the stationary phase, right? The deceleration phase itself in the batch system, right? In the batch system, the deceleration phase itself cannot continue indefinitely. It has to stop at some point. Let me go back to the diagram for you to have a clear picture. Let's go back to stage 4 here. Stage 4 itself, culture, the batch system will not remain there indefinitely. Eventually, it enters the stationary phase, where the growth rate equals the dead rate. Now, one thing I would like you to understand it is the conditions, the parameters that triggered the onset of deceleration phase are likely to be the same parameters that will force your culture to enter the stationary phase. I repeat, the conditions that triggered the onset of the deceleration phase are likely to be the same conditions that will force the system to enter into the stationary phase. In other words, if it was, go ahead, Nolu. Question? Okay, if it was the depletion in glucose that has made the cell to enter the deceleration phase, it's highly likely that the same depletion of glucose will force the cell to enter the stationary phase. If it is the lack of nitrogen that's forcing the cell to enter the deceleration phase, it's highly likely that the lack of nitrogen will still force the cell to enter the stationary phase. Now, what happens to the stationary phase? You have a number of cells that are dying. You have a small number of cells that are multiplying. In other words, the death rate equals the growth rate. That's why the cultures is into this horizontal stable line. Okay, we have this horizontal stable line because the number of cells dying equates the number of cells being produced. That's what happens in the stationary phase. Cells are metabolically active. That is, we have a number of compounds as well being produced. Like said earlier, those compounds are not growth link. Okay, they are not growth link compounds. And again, if you look at the diagram, cells, your culture in the batch system will not remain indefinitely in the stationary phase. It will eventually enter the dead phase as well, right? It's going to enter the dead phase at some point. Just to recap what you've done, cells start with the lag phase, acceleration phase, exponential phase, deceleration phase, where growth reduces, stationary phase, and eventually dead phase. And some of the important phases, which I've mentioned with regard to the production of antimicrobial, deceleration, and stationary phase. Okay, this is what I would like you to keep in mind here. Okay, just again to refresh your mind that during the stationary phase, you have a slow metabolism, right? You have a slow metabolism, and cells are actually producing a number of antibiotics or antimicrobial as well as the endospores. And the length of that phase will depend on the type of microbes you are dealing with. Now, if you look at the previous graph that we have here, if you look at this graph here, this shows you the type of product that are linked with growth. You see that the production rate of this product clearly align, there's quite a great correlation between the rate of production of this product. I'm referring to the dotted line. Then there's a huge correlation between the growth associated product and the growth rate of the cell. Unlike those are not growth associated. You see that the productions of those products, we have your dotted line, is not correlated with the rate at which cells are growing. In the contrary, you actually have huge amount of those products when cells enter the deceleration and stationary phase. Now, if you look a little bit at the beginning of the dotted line here, that corresponds at the time at which cells started producing this kind of product. These are non-growth link product. If you project it up, you realize that it is at the deceleration phase that the production commenced. At the growth phase, exponential phase, there's no product formation. But at the deceleration phase, that the production started and proceeded throughout the stationary phase. That gives an idea between the growth associated, the different phase of growth, and the kind of product associated to those phases. One of the questions which I can give to you is the following. One of the possible questions could be for you to give us example of products that are growth associated, example of products that are non-growth associated. Now, what I would like you to understand here again to understand is the advantage and the limitations of the batch system and where it can be applied. Okay, to understand the advantage of the batch system, one of the key advantages of the batch system is that it reduces contamination, right? It reduces contamination because you can easily sterilize all the equipment, the nutrients, the reactors, and so on. That is, you have the possibility of reducing the contamination. Now, if you look at the disadvantage, for example, you're going to spend much more time sterilizing. Batching is referred to as batching. You spend much more time sterilizing those nutrients, sterilizing those reactors, unlike other fermentation mode, right? Here you can prevent sterilization. So you can prevent contamination easily in the batch mode, but you have to sterilize very often. Now, let me ask you a question. Although we haven't covered things like continuous system, but do you think productivity here will be higher or lesser compared to other systems? Do you think productivity will be higher or lesser compared to other systems whenever you use the batch mode? Are you going to have higher productivity or lower productivity? Obviously, you're going to have lower productivity because...
Lower.
Go ahead, please. Is it?
I was going to say, I think it's lower because of the condition that we can't add nutrients and that we can't remove any of the broth.
Thank you. That's the new. Now, you're going to have lower productivity majorly due to the fact that you have to produce one batch, and to produce one batch means sterilizing all the things we saw at the upstream phase, sterilize the nutrient, sterilize the reactor, inoculate the reactor, carry out inoculum development, carry out the bio process itself, right? All the activity of the upstream will take place. Then you move to the downstream, which you we separate the product and purify. When you finish one batch, again, you start sterilizing again the reactor for the next batch, sterilizing the nutrients, carry out a new fermentation batch, go back into the downstream. That is to go batch by batch. Therefore, the unproductive time, which is referred to the time you spend sterilizing the nutrients or removing your product, the unproductive time becomes longer. At the end of the day, it doesn't give you, the productivity is lesser in the batch system compared to other production mode. One of the questions which I gave to students was sometimes back was to discuss advantage and limitations of the three mode of production. I'm referring to the batch, the continuous, and the fed batch, right? Yeah, obviously the applications we're going to use the batch systems majorly when you are producing those kind of products that you want to reduce the risk of contamination. Okay, when you produce those kind of products that you want to reduce the risk of contamination, batch will be much more suitable for those kind of processes. And there are also a number of applications which I've placed in your slide material, and I hope you're going to spend a couple of time reflecting on those advantages, limitations, and area that it could be applied, where the batch system could be applied. For your information, when you move to the industry, you're going to realize that in actual fact, batch mode is widely used, despite the limitation, the low productivity that we have just discussed right now, is widely used in the industry. Now, let's look at something much more important again, and I would like you to pay attention and understand. If you're getting confused at some point, please don't hesitate, stop. I will explain until you understand what I wanted to understand. Now, let's have a look at this flask. We have approximately 5 flasks here, all contain different concentration of nutrient. Let's call it glucose, for example. If I inoculate this flask with the same size inoculum, that is, I put in the same amount of, let's say, Saccharomyces cerevisiae in each of these flasks, and I observe the growth rate over time, or better still, observe the growth rate in each of the flasks. In other words, I could come out with a table that shows the initial nutrient concentrations and the growth rate, which we'll be calling mu for this purpose. We're going to call the growth rate mu. The growth rate that we obtain here with the 2 grams of glucose is likely to be different from the growth rate that we're going to obtain with 4 grams of glucose and the growth rate we're going to obtain with 6 grams of glucose, and so on and so forth. Now, with the table that we have, keep in mind, we have a table that gives us the nutrient concentrations and mu value, mu, the specific growth rate. If I decide to plot a graph of that nutrient concentration here, S, and mu in the y-axis, I'm going to have a line that has this shape. Is it clear to everyone at this stage? Tenley, Brian, is it clear to everyone? Or you want me to go back to it again? Who's not getting the concept yet? Okay, let me proceed. But if you feel at some point that it's not clear, let me know. I'm going to go back to it again. Now, what you have here correspond to the monode equation, the equation that links the specific growth rate and the substrate concentration. I would like you to write it down, that the relationship between the limiting substrate concentration and the specific growth rate can be described by the monode equations based on the experiment I've just given to you. Okay, write it down somewhere. It's in the slide material I've given to you as well. That the relationship between the limiting nutrient and the specific growth rate, the link they have can be described by this equation, and this equation is obtained from this experiment in which you have different batch cultures that differ with the substrate concentration, and you are measuring mu. Then you plot the observed mu value against the substrate concentration. That gives you a graph that has a shape or that can be fitted with the monode equation. Now, the reason why I copied this equation because it helps us to obtain some useful information in the batch culture system. Okay, it helps us to derive some key information in the batch system, which we're going to derive in subsequent slide. Now, of course, the monode equation that you have here, mu, the specific growth rate, equals mu max. Mu max refers to the maximum rate of growth of the cell. Okay, equals mu max multiplied by S, which is the substrate concentration, divided by S plus Ks. Okay. Take a snapshot of that equation because you're going to make use of it. I can assure you that in one of the exams, you have to explain something that have to deal with this equation. Of course, I'm not going to ask you complicated computations because I promised you at the beginning of this lecture, I will make it as simple as possible. Okay. It will be the simplest, it will be very simple for you. All right, great. We're back with our equation, monode equation here. There are a number of informations that we can derive from it. The first very visible information is what? Mu max. If you project where there's a plateau of your graph, you project it back to the y-axis or the mu axis, we're going to have what is referred to as your mu max. Mu max that you have here is in actual fact the maximum rate of growth of the cell, or it's called the maximum specific growth rate. That is the maximum. Take it as the maximum rate of growth of the cell. They can't go above that. We already obtained one very important parameter, mu max. Now, we also have another parameters that can be obtained by finding half the value of mu max. That is, what you have as mu max, if you divide by 2, and you find a corresponding substrate to that, that will give you your Ks value. And Ks value is a monode constant. Now, what you have to work out the monode constant in this equation, it will provide a very good information for us in subsequent slide. The monode constant will help us to understand the affinity of the cell to the substrate. It will help us to know if the microbes we have, they love the substrate or they don't love it. They like it or they don't like it. That's what we're going to find out. That is, we already have two nice information from that experiment. We have mu max that give us the maximum specific growth rate. You have Ks value that help us to understand the affinity of the microbe to the substrate. What I mean by affinity, I would like you to interpret it as, listen everybody, one easy way to understand what I mean by affinity is, do microbes like or they dislike the substrate being fed in the reactor? Who has a question at this stage before I proceed? Hello, class. Is there any question you'd like me to clarify here? Okay. When you go to the slide, if you have a question, please, I'll come back to it, okay? Now, here comes, please spend 30 seconds to have a look at this important graph. I look at the section mark A and B. I will give you 1 mark, bonus mark, if you answer the question I'm going to ask you with the correct answer. Spend some time, observe this graph. But before I ask you the main question, let me clarify something. Is this graph the microbial growth curve? Are we dealing with microbial growth curve here or not? Is it the microbial growth curve? The microbial growth curve, what I'm asking you is, these two graphs, are they the same? Are they similar? Is it the same graph that we have? In your left and your right. Remember, what you have in your right gives you the different stages of growth. And in your y-axis, you have the optical density that corresponds to the biomass concentration. In your x-axis, you have the time. Whereas what you have at your left, in your x-axis, you have substrate concentration. In your y-axis, you have specific growth rate. In other words, these are two different graphs, okay? That answered the first question. These are two different graphs. Please keep in mind. I hope we're still within time. Okay, great. Keep in mind, we're dealing with two different graphs at this stage. Now, I'm going to ask you a question now, the one that's going to give you the 1 mark I promise, if you give me the right answer. The segment A that you have here, of course, the segment A is what is within this range. Compared to the microbial growth curve that you have at your right, segment A corresponds to which stage of the growth? Let me ask it. Does it correspond to the lag phase, exponential phase, deceleration phase, or stationary phase? If you answer correctly, you're going to have the 1 mark. Segment A. Of course, we are dealing with two different graphs, but they have some common points. Two different graphs, they have some common points. I like telling students the area which I'm going to assess them. And this seems to be one of the areas which I will assess you. Now, the question is, segment A that you have here, does it correspond, which stage of this microbial growth curve does it resemble, does it correspond to? We want to try. We want to attempt. Does it correspond to exponential phase, deceleration phase, stationary phase? What does it correspond to? Michael, do you want to try? Or Tereshna? You have 1 mark.
I'm not sure, sir.
I would think it's the log phase.
Which phase again, Tereshna? Which phase?
The log phase, exponential.
Log phase,
Log.
exponential.
Yeah.
You mean exponential?
Yeah, exponential.
All right, okay, we're gonna come back at Tereshna. Michael was about to say something. Then
sorry, I was saying I wasn't sure.
Sorry?
I was saying I wasn't sure. I wasn't. It's a bit
Go ahead.
spotty every now and then.
Yeah, but what phase do you suggest? Do you think is likely to correspond to?
I think it would also correspond with the exponential phase.
Okay, I'll come back to you. Nolu Yolo, what phase, what do you have in mind? Then Api will tell what she thinks as well.
I think it's exponential phase.
Okay, Apiwe, go ahead. What do you think? Remember that you have one mark that you can grab easily. That will help, especially if you are the borderline. Apiwe, what is your take on this? Okay, all right, perhaps she's not connected. Now, let's have a look at this. You said exponential phase. Now, by definition, I repeat, by definition, exponential phase is a phase where cells have nutrient in excess. And exponential phase, we said at exponential phase, cells are growing at mu max because they have too much nutrient to consume. That's the exponential phase. If you look at section A here, do cells have enough nutrient to grow? Do they really have enough nutrient in stage A here? Class, do cells have enough nutrient on this stage A here? Absolutely. If you project back to the axis of S, you realize that substrate was lesser. In other words, cells did not have enough substrate to grow at mu max. But if you look at B, which the substrate concentration was high already. And again, we projected segment B to the axis and said that was our mu max. Therefore, based on that, segment A corresponds rather to the deceleration phase because cells do not have sufficient nutrients. Segment B, if you project it to the microbial growth curve, it is a phase whereby cells are growing at mu max. Therefore, the B that we have actually corresponds to the log phase or exponential phase. I would like you to reflect on that and understand it clearly. Sorry, don't make a mistake. We have here in your S-axis, sorry, in your X-axis, you have substrate concentration. And obviously, under the segment A, you don't have enough substrate. Substrate is lesser. And cells are struggling. That's why each time that you increase the substrate, if you look at it, if you increase substrate, the growth rate increases. You increase substrate, the growth rate increases up to a point whereby if you further increase substrate concentration, the growth rate becomes constant because cells are already growing at mu max. Who has a question there? Who has a question what you covered here before we? Longdeka, is it clear to you? Or you want further explanation? No Monday. And Brian, is it clear?
So it's not really clear for me.
Okay, I'm going to do this. I'll allow you to reflect on it again. Then at the next lecture, I'll come back to it for further explanations. Okay, I would like to reflect on it again. At the next lecture, we go through it again to see if you have digested it. But if you look at it clearly, you realize that S is lower. Always keep in mind that what you have here under your X-axis is a substrate concentration. And it starts from 0 or from the lowest amount, and it increases. And what you have on your Y-axis is the rate of growth of the cell, the specific rate of the cells. And as you're increasing the substrate in this axis, you realize that cells are growing faster. If you increase the substrate, they are growing faster up to the point whereby further increment in the substrate concentrations do not make cells to grow because they're already growing at mu max. And if you look at your microbial growth curve by the right, by definition, mu max or the maximum growth is obtained only when cells are at the log phase. When cells are growing maximally, that's where they also have the mu max. And if you look at your deceleration phase on the microbial growth curve, you have to look at your deceleration phase, which is somewhere here. We said deceleration phase was a scenario in which there's a depletion of nutrients. Cells are about to starve. Now, if you try to project it back to the graph by your left, what is the time that they don't have enough nutrient, that they have what could be referred to starvation, is only the segment A, where they don't have enough nutrient. Therefore, that A will correspond to our deceleration phase, whereas B will correspond to our exponential phase, when cells are growing maximally. All right, okay, I will stop here for today, and I will confirm over Zoom whether we're going to have, sorry, I'll confirm with the class rep whether we're going to have the Friday lecture, but it's highly likely we're going to have it, unless if we're not going to have it out, the class rep will inform you. But for now, we'll keep in mind that we're going to have the lecture again on Friday. Then we can look at the questions. Okay, the question was rather great. I could actually see that somebody got the right answer. Jezreel, he or she got the right answer actually, so that corresponds to deceleration phase. Okay. Somebody actually get the right answer that corresponds to deceleration phase. All right, thank you very much, and I wish you a lovely day. Go through the material. I've also opened a YouTube, there's a YouTube channel on this page or your model page that contains a number of videos for this module as well. Okay, if you go there, you're going to see a number of videos that explain different concepts on this module. Then your model also, you have the material that was the material that covers the batch system, and I promise you to put another material that will cover the continuous, another set of material that will cover the fed batch, so that you'll be fully grounded in those production mode or the fermentation biotechnology. Thank you very much, and we'll meet again at the next lecture.